All right, so here's the additional review. It's optional. Kind of one of those, if you want to do well on the test, do the review. One who's doing work is the one getting smarter. If you want to learn math, you have to do math. So here we go. Given the graph, identify the following. My y-intercept looks like it happens right here. So 1, 2, 3, 4, 5, 6. We're going to say over 0, up 6. My x-intercepts look like they're 1, 2, 3. And this is a double root. So -1. Oh, I forgot this one. That's not. Okay. So 1, -1, -2, -3. So it looks like over -3 up 0, over -2 up 0, and over +1 up 0. So my zeros, my roots are my solutions. X is equal to -3, -2, and +1. You have a double 0 at x is equal to +1. All right, so then if we wanted to know the factors that gave us these zeros, that would have been x plus 3 is going to give us that 0. X plus 2 is going to give us this 0. And x minus 1 is going to give us that 0. And don't forget, when it says including multiplicity, guess what? X minus 1 is going to be our double factor. It's to the 4th degree. This is an x to the 4th graph. So I need 1, 2, 3, 4 solutions. Okay, my degree is going to be even because both of the endpoints are both going the same way. They match. All right, it's a degree of 4. My leading coefficient is going to be positive. And then when I look at my end behavior as x approaches -infinity and positive infinity, they both end in infinity. Okay, number 2, enter the equation into the calculator and use the statements A to E to describe the roots. Whether it has exactly 1 or exactly 1, exactly 2, exactly 2 imaginary. So these are the ways that we can describe. So these 6 are going to have to be entered into the calculator. All right, so I'm going to turn on my calculator and we'll do this side first so we can make sure you guys can see it. Okay, so I'm going to clear it out and I have x minus 2 to the 3rd power. So when I look at that graph, when I look here, ooh, isn't that interesting? That's going to be 3 real roots. When I go to the table, every single one of them happens at x is equal to 2. So that's going to have exactly 3, it has a multiplicity of 3, so it has exactly 1 distinct real root, but it has a multiplicity of 3. Three distinct, okay. So when I look at B, let's change our graph, and I go to x cubed plus 1. So when I look at this graph, there's my graph, and it looks like just 1 distinct real root, and then it has 2 imaginary roots, because here's where the turnaround happens. It has 1 real root, it doesn't bounce. 1 distinct real root, 3 distinct real roots, exactly 1 real root, and 2 distinct imaginary roots. We're going to go with E on that one. All right, let's look at this one. x to the third minus 3x squared plus x minus 3. Right. So when I look at the graph, check out that. Here is 2 imaginary and 1 real. We would call that 1e also. All right, let's look at these. We're going to have x to the third. Oops. X to the third minus x squared minus x minus 7. Let's see what that looks like. It looks like 1 real and 2 imaginary. All right, let's take a look at this one. The opposite of x to the fourth, clear that out. The opposite of x to the fourth plus 4x squared minus 2. And what do we have here? All right, so I have 1, 2, 3, 4 places the graph is crossing. And I'm going to go with 4 real roots. We'll call this F, 4 real roots. Call that F. 1 distinct, 2 distinct real, 2 distinct imaginary, 3 distinct real. Definitely looks like 4 distinct real to me. All right. Let's check out this one. 1 divided by 2 x to the fourth minus 2x to the third plus 7x squared plus 5. Let's see what this one looks like. It's a 4th power function, and I'm not seeing any real, so we're going to have 4 imaginary. Boy, this is a lousy worksheet. I see 4 imaginary. If I wanted to zoom out and look at a bigger picture of the graph, I don't see it ever crossing the axis. It's not going to come down here. It's going to continue and it never crosses that axis. All right, sketching the graph. When we look at this, we can go ahead. Please don't feel like you can't enter it into the calculator. Absolutely. So we have x minus 1 to the third power times x minus 2. So it's going to be a 4th degree function. When we go ahead and graph, we should see 3 turns, or not. All right. This is going to be here a triple root. So this is going to be a triple root where we add x is equal to 1. And then we should here have a root at x is equal to -2. I'm wondering if I typed that in right. X minus 1 times, there's my problem. It should be x plus 2. That should look better. 1 root here, that looks much better. Here's our triple root. When we have a triple root, then it just spends a lot of time instead of bouncing. Like the double root, triple root, it just ends up kind of flattening out there. Okay, Our first question is going to be our y-intercept, and we need to sketch the graph. So we'll go ahead and say that over 0, down 2, and we can go ahead and fill that in. And then we have our solutions are at -2 gives you an output of 0, and 1 gives you an output of 0 with a multiplicity of 3. Whether you call it a triple root or a multiplicity of 3, it doesn't matter. It's the same thing. Okay, at -2, there's a 0, and at +1, there's 3 zeros. So if you wanted to graph any other points, you could. -1, 1, 2, 3, 4, 5, 6, 7, 8. And over 2, up 4. But just by looking at the generic shape, you can see this graph comes down like this. And then it comes up through here. And that's okay to be good enough. All right, our triple 0 is at x is equal to 1. It's an even function because I have 4 and my end behavior matches. It is a 4th degree. My leading coefficient is positive, and I am approaching positive infinity in both directions of x. My domain is going to be all real numbers that can go in, and my range is going to be everything above this floor as my output. So when I look at this, -1, 2, 3, 4, 5, 6, 7, 8, -8, oops, I can box that, is my smallest value, and positive infinity will be my largest. All right, write a polynomial function in factored form that has the given zeros and a leading coefficient of 1. Do not leave any factors with I in your answer. Okay. Factored form means that these are my solutions, which means this, and that are my factors. X is equal to 1, so x minus 1 is equal to 0. X is equal to -2, so x plus 2. And all we need to do is to put that into function form is set it equal to y. X times x plus 2 times x minus 1. So that is a 3rd degree function. We can call it a cubic. All right, a 0 of 3 with a multiplicity of 2 and 2i. All right, so let's talk about what this means. If I have a multiplicity of 2, that means that x is equal to 3 twice, which means that x minus 3 is a factor twice. If x is equal to 2i, remember imaginary roots always happen in pairs, which means that x is also equal to minus 2i because that whole plus or minus thing. So when I have my factors, I have x minus 2i and I have x plus 2i, which is going to give me 4 roots, x minus 3 squared, and I have x plus or minus 2i. So that is going to be a 4th degree or a quartic function. And whether I put my y on the left or right, it doesn't matter. Okay, so if x is just equal to 2i, remember x is equal to 2i and x is equal to negative 2i. So this comes from x minus 2i, this comes from x plus 2i. So my function is x plus or minus 2i, and that is going to be a second degree or a quadratic equation. A 0 with a multiplicity, a 0 of 2 with a multiplicity of 3, and negative 4i. So that means that my 0 of 2x is equal to 2 3 times. So that's x minus 2 cubed. Negative 4i is one of my solutions, and remember, if x is equal to negative 4i, x is also going to be equal to positive 4i. My imaginary roots always come in pairs, which means that x minus 4i and x plus 4i are going to be solutions, so I can write them together. So my y is equal to x minus 2 with a multiplicity of 3, and then x plus or minus 4i, where that's two solutions there, so that gives me a 1, 2, 3, 4, 5. That's a fifth degree or a quintic polynomial. Okay, so before we go on to the next page, we need to go back and read our directions, because guess what it said? Do not leave factors with I in your answer. So this one is good, but these two, these three, we need to spend some more time on. All right, so when I have x plus or minus 2i, we can't have I in the answer. So we have to figure out what factor did this answer come from. So what I want you to do is think about x plus 2i and x minus 2i, and we're going to FOIL them to give me my factor. So x times x is x squared, minus 2ix and plus 2ix. You can always count on getting a zero pair because it's a minus and a plus. So then I end up with x minus 4i squared. I squared has a value of negative 1, so negative 4 times negative 1 is going to be plus. So x squared plus 4 is the answer I'm looking for. So it's kind of cool how they work out, and you can understand we're not going to leave imaginary numbers in, but we can predict that came from an x squared function with a positive that couldn't be factored. So it's kind of cool when you look at how these patterns work out. So when I put my factors side by side, I know x times x is x squared. Here's my minus 2ix and my plus 2ix. They're going to make a zero pair. So that's going to give me minus 4i squared. I squared has a value of negative 1. So that makes each of these positive. So again, I have x squared plus 4. So I'm wondering if you can make a prediction about what's going to happen here. So we know this is going to be a squared, and we know this is going to be a plus. But can you look at the patterns that happen with these coefficients that gave me this prime quadratic factor? So we have plus or minus. So if it helps you, go ahead and write it out. And we'll get rid of this minus. So we have x plus 4i and x minus 4i. So x squared minus 4ix and plus 4ix are going to cancel out. So we get minus 16i squared. I squared has a value of negative 1. So you got it. X squared plus 16.